Greetings everybody. We're going to talk briefly about describing reactions using Lewis symbols and the infamous Octet Rule. So before we go down that pathway, there's a few things that I think are very, very important for y'all to know and remember, kind of keeping these sort of in the back of your mind when we're working through this idea. So the first thing I want y'all to remember is, number one, fundamentally, at its core, all chemical reactions involve the forming and or breaking of bonds. Every bond involves what we call the sharing of electrons, or the sharing of valence electrons. I want to be clear. If a professor or maybe another chemistry teacher saw this video, they would probably be flipping out right now. But hang with me, and there's a reason why. But trust me, every bond out there involves the sharing of valence electrons. It's important for y'all to know, though, that we classify bonds according to the degree to which the two atoms share their electrons. So all atoms, by the strictest definition, share electrons. It's just the degree to which they share electrons can widely differ. You can actually think of this sort of like a spectrum, if you will. So sort of like a number line, if you want to. Since we classify bonds according to the degree to which the two atoms share electrons, then your spectrum goes from no sharing to perfect sharing, right? So I'm going to put perfect sharing over here on my left just because I feel like it. And so perfect sharing, right, is where you have these two electrons aren't found on any one atom more often than the other. The other end of the spectrum, obviously, is going to be no sharing. No sharing, of course, means that one atom stole another atom's electron. So between these two ends of this spectrum, we would have unequal sharing. Every bond, in the exception of metallic bonding, all bonds that we're going to be talking about can be thought of in this way, as these two spectrums: perfect sharing, no sharing, and then you've got everything in between. So let's talk about no sharing for just a minute. A great example of no sharing would be the formation of sodium chloride from its elements. Let's go back a step. What's the guiding force? What's the motivating factor? What's the desire, okay, of these atoms to want to do this anyway? Why would two atoms actually find it more energetically favorable to form bonds or to go through this whole process of sharing or exchanging electrons? It all actually goes back to what you saw last week. So one major point from last week was for y'all to recognize a big connection between the stability of a noble gas configuration by looking at the ionization energy data. It's so stable, in fact, that it is energetically favorable for atoms, any atoms, like these two atoms. They want to get there because, again, energetically favorable just means that it's lower in energy. It's a much happier place for these atoms to exist in. So they're going to try to achieve that. Sodium is going to wind up donating its electron. Why donate its electron? Well, we'll get into more detail a little bit later, but basically chlorine is a bully, and this will not be any sharing. In fact, chlorine's going to pretty much beat up sodium and steal its lone valence electron. So this little guy right there is going to come all the way over here. Something really awesome just happened, right? Chlorine just obtained 8 valence electrons by stealing sodium's lone electron. But sodium also obtained a completely filled energy level. By losing its lone electron, look at where sodium's at on the periodic table. It's in that first group, the far left group. It lost an electron, which gives it now a configuration of that of a noble gas. Because if you do the electron configuration for sodium ion, you would see that it now has 8 valence electrons. So does chlorine. So going way back up here to the tip top, the Octet Rule students, octet obviously coming from the Greek prefix octa, meaning 8. So it's not a perfect rule. There are exceptions to it, but predominantly it says this. It says that atoms will tend to gain or lose electrons to achieve a valence of 8 electrons. So students, y'all are actually very familiar with this. This is actually what we call ionic bonds. Ionic bonds are no sharing bonds. They don't share electrons. One gets stolen. So what's going to happen is, I think, pretty clear. This guy is now positively charged, which feels a net attraction to that guy who's now negatively charged. They come together right now. All right. Right, something like that. So now they come together and they stick together because they are oppositely charged particles. Let's talk about a compound that doesn't have ionic bonding. So why don't we take a look at someone like carbon tetrachloride. Unlike the previous example where chlorine was strong enough to strip that lone electron from that sodium, chlorine just doesn't have that ability when it's bonding with carbon. Carbon does hold on to its electrons pretty well. Another way stated, they're going to have to share their electrons. And so what ends up happening is something pretty cool. This lone electron comes over here and gets to make a shared pair of electrons with this guy here. So this guy gets to come over here too, and the two together become what we call a covalent bond. A covalent bond is where two atoms are sharing their electrons. And notice that chlorine only needs one valence electron to have a filled valence shell of 8. And so it's going to share 2 electrons to get the job done. Which 2 electrons? Well, those 2 that we were just talking about. Now what's awesome about this is, notice the way that I've drawn this. Okay, so in the way that I've drawn this, it's to be read that this chlorine now has 8 electrons around it. But that's a shared pair, which means that that carbon gets to count it as well. So this carbon atom has 5 valence electrons now. But if you remember, the octet rule says carbon wants, you guessed it, it wants 8. So what are we going to do? Well, as it turns out, we need another chlorine, don't we? So notice at this point now, carbon has a grand total of 6 valence electrons. Well, this pattern is going to continue until carbon has its 8. So at this point, hopefully you can see that every single person in this diagram has 8 valence electrons. This chlorine has 8, and that guy has 8, and this one 8. This one has 8, and of course carbon now, he has 8 valence electrons